Hello, everyone. Welcome to today's session. And today we'll be talking about discriminant analysis and classification methods. On our last session, we already performed some classification analysis and then created predictive models based on that classification using algorithms like decision trees or random forest algorithms. So in essence, those algorithms are quite similar to the ones we'll be talking about today. They also belong to this branch of machine learning that is called supervised machine learning. So before we start with some new things, let's just make small recapitulation of some things we talked about before. So we were talking about labeled and unlabeled data. And last time we saw that unlabeled data in a machine learning kind of way of thinking or statistical way of thinking is the data that has unique labels. So we can observe rows, we can observe columns. All the labels are unique, even though we have, for example, here normal, normal, normal. Aside from that, we also have this SRR, accession number, which is unique for each sample. So if we observe the whole name, it's unique. On the other hand, we had label data that has this same ID column, but it also has this class, which has absolutely same names for various samples. For example, we have 7 or 8 normals here. They have absolutely same names. We have luminals, basals, etc. So this column is called a class, and it's used to categorize data. So in essence, this is the difference between labeled and unlabeled data. Unlabeled data is not data that has no labels in some general way. If you had absolutely no labels in the data, well, that data set wouldn't be very useful for any analysis. So unlabeled data is the one that has unique identifiers in their naming labels. On the other hand, labeled data has also those unique identifiers, but also has this labeling of the classes which contain non-unique names, and they're used to categorize data in that same category, for example. So we saw that in supervised machine learning, we need a data set that has labeled source data. So data is not yet separated, it's not yet inputted into this classification model, but it has labels. And we use supervised machine algorithms to actually create the classification and prediction model, and we call that model a trained model. So we can use a trained model to predict new data. We could have new data with no labels, but we could use the same training data set or the same training model to actually create predictions for this new data. Another important thing that I also want to mention again is that when conducting supervised machine learning, it's very important to validate the trained model. By saying that, I mean that trained model is self-validated, but it should also be validated on other data sets. There are multiple ways of validation, and we talked about some of them before. Why is this important? Because when we conduct unsupervised machine learning, we derive most of results from the data itself. We're not creating some predictive models based on external information, and then we see how can we relate that external information to our data. In unsupervised machine learning, we're deriving most of the things from the data, and the probability of making a mistake is much smaller when we take that approach. But if we take approach that we have a classification and we want to predict each object in the data set based on that classification, we could have some accuracy issues. Sometimes we can create an inaccurate model, right? So we can make mistakes in predictions, and that is very important because if you create a predictive model, you want to have high accuracy. That is the whole point of making a predictive model. If you have a bad predictive model, well, you shouldn't create it at all, right? So if your data does not allow you to create a good predictive model, the best thing to do is not to predict anything there at all. You should take other approach or take other data or include some other form of analysis to create better predictions. So having a good and accurate predictive model for the classification that you're creating is a very important step. And we'll talk about this a lot today. So today's session will focus on using different methods to validate the trained model from different angles, and we'll also talk about other methods that we won't be using today practically, but they exist and we'll also mention. Before I go to new classification models, I just want to remind you that we performed random forest last time, and you saw that we actually selected few genes that could potentially be important for the disease we were analyzing, which was DCIS breast cancer. But each algorithm has multiple variations. So you could have a plain random forest model, or you could have models that have other features, like, for example, multi-run random forest, which is practically the same as random forest. You just have the option to run it multiple times in a single pipeline. Why would we run something multiple times in a single pipeline? Well, this is something that I'm mentioning for the first time now, and it's also very important since we're learning about machine learning a lot in these few sessions. Uh, you could take any of those algorithms, especially, for example, k-means or age clustering, or you could take random forest as well. Uh, if you take those algorithms, if you load the data set, if you load data in the pipeline and run the pipeline, you will see that very often you will have a situation that if you run the same algorithm twice or three or four times, you will get slightly different results. Those results will generally be pretty much the same, but with small differences. And this is because we're talking about machine learning. We said that each machine learning algorithm has repetitions of the algorithm, and for example, we have 1,000 repetitions, and the algorithm will learn something from those 1,000 repetitions and create optimized model for us. So each time you start these iterations or repetitions, you might have a different starting point, and then you might have a little bit different outcome from those 1,000 repetitions. So results could vary a little bit because we're talking about the learning aspect of the algorithm, but those are some very small variations. And random forest multi-run is meant to actually decrease even these small variations. So you run it a couple of times, you could run it many, many times, and then you see which run is most frequent and which result is with most confidence. But as I said, even if you run it just a single time with a large number of iterations that it does on its own, you will get very confident results. But there is one very important thing here: you will get very confident results if you have good data. If you don't have a good data, no matter how good the algorithm is, your results won't be very accurate. So one of the most important things, and we'll be talking about this a lot during the program, one of the most important things is having good data. So if you have a data with just 10 genes or 50 genes and just a couple of samples, you won't have enough statistical power to derive some accurate results or create some accurate predictive models. So it's very important to have a lot of samples a lot of replicates of samples, a lot of genes included in the data set, because if you have most of the genes from a single genome, then your probability of missing out on some important genes is very low. On the other hand, if you have just 2 or 3 samples, you can't really compare them too much. But if you have 50 samples or 100 samples or 1000, you can get more confident results. So today we'll be expanding on the classification issue. What we did last time is we found some cutoff values, and we used those cutoff values in decision trees to actually make a decision on which branch of the tree to go. And in the end, we used all those branches to create a predictive model based on a couple of genes. The most important, by my opinion, the most important aspect of random forest is that it doesn't just create a classification or prediction for a scientist. It actually selects features. It selects genes that are important. So we saw that it was able to select those 20 genes in the end that could potentially have some importance to the DCIS. It doesn't have to be the case in 100% of situations. Sometimes random forest will give you results and you'll find that just some of the genes are relevant, some aren't. But generally, if you narrow down from 22,000 genes to just 20 genes, then it's a lot easier job to actually conduct the analysis to some new levels. Another aspect of random forest was classification. We saw that we had, as I remember, 92% accuracy in that trained model. So the model was creating its own classification. And how it's done, I'm just gonna get back here to show you that. How you validate the trained model internally without using an external data set. Well, simply you have label data, you have your initial data set, right? You have classes. So what you do is you run the algorithm and you create the trained model that would make that classification. What you do then is you take the same data set, you take the same data set, you just remove the labels. So same data set without the labels, and then you take the trained model and test it on the same data set. So in essence, we don't have to do this because random forest algorithm does this on its own. So each time you run it either in RStudio or Python or by running the pipeline on tBind platform, the model will self-validate. It will create that file that is called trained stat or something like that, and you will have the confusion matrix and overall accuracy. So our overall accuracy was about 92%. So the important aspect is the classification. So you're using the trained model to classify data based on some statistical features that you have in the data. Random forest uses decision trees to classify data, but there are other forms of classification and other statistical methods of creating some decision boundary between subclasses or classes in the data. You don't have to create a decision tree. There are methods, for example, that draw a line, some imaginary line on the plot, which would be used to separate two types of classes in the data set with the highest accuracy. This line could be straight. This line could have some other shape. Generally, if you have a straight line, then we're talking about linear models. If you have some other shapes like the one you see here, that is something that corresponds to a quadratic shape or exponential shape. So depending on the property of the data we are using, we could have different shapes of these discriminant lines. So discriminant lines will be used to actually decide, algorithm uses them to decide which object should be assigned with which class. So if some object is, for example, on the right side of the line, it is assigned with the blue class, for example. If it's on the left side, it's assigned with the red class. But you see that even here, the accuracy is not 100%. You have some blue values that are on the left and red values that are on the right. So accuracy is also the issue whenever you conduct any classification or any predictive model. Accuracy is always something that you have to pay special attention to derive more validation in the results. So we'll be talking about two algorithms today, which are called LDA and QDA, as you could see on that initial image. So LDA stands for Linear Discriminant Analysis. And if you analyze the name, you could pretty much derive most of the information from the name itself. So linear means it's linear. We are dealing with the straight line. You can see that from the image. And it's discriminant. So that straight line is actually being used to classify data in different classes. As you can see on this image, you have some LDs, which are linear discriminants. You have LD2, LD1, and similarly to what we did in the PCA, we could use them to plot values based on them. On the other hand, you can see here in the lower right corner a quadratic discriminant line, which is very similar to linear. We just use a quadratic function. So we are, instead of using values that are on a linear scale, we are just using exponential scale. We were talking about logarithmic scale. Well, opposite to that would be exponential. So if you use exponential scale to separate classes, then you would have this line as you can see. So they're very similar with just some different statistical properties that are being used. So in the end, you could create a plot which actually shows you how is your data separated, and most importantly, which classes are assigned to which objects in the data. So you can see here linear, quadratic, diagonal. They're very similar, right? So we have very similar patterns with some small differences. And what you can see here are those same ellipses that we use in PCA, those confidence ellipses, but classification allows for a value to be outside of the ellipse, but also be assigned with some class, because we're drawing discriminant lines and we're not using ellipses to create the classification. There are other methods we'll be talking about today, so I'm just giving you some theoretical perspective, but we will perform them on T-Bio platform. So support vector machines with linear kernel. I know that this term might sound a bit complicated, but it's not actually. In the analysis that we talked about before, we had just the line that separates two objects in the data. But here, we're not just having one line, we're having three lines. So we have some central line which separates the data, but then we also have two lines which are called support vectors, and these lines are kind of they're transformed in a way that they're as close to data as they can be. So they're not just between these objects, they are close to the objects, and they create some buffer space between this central line and these vectors, right? So you're not just having one line, you also have another two lines which are called support vectors, and they're like supporting the whole clusters, right? So they're at the edge of the clusters, and they're supporting them. It looks as if they're supporting them because they're at the very edge. On the other hand, they're creating this space between the classes, between the clusters, and this space is very important because this space is giving additional layer of confidence to that central line. So no value is actually in that space. That is an empty space, and all the values are on different sides. So in this way, we are increasing the accuracy of having just one discriminant line. We are adding two support vectors, these two additional discriminant lines, to actually create this buffer zone that would increase the accuracy of the model. Why are these support vectors also have this term machine. Support vector is not a machine. It's just a term that we use in machine learning. In essence, support vectors are statistical properties that are presented as these lines, and you take two lines and create them in a way that they support the border objects that have most extreme values. So support vectors should add another layer of accuracy into the classification. We also have another issue here is, remember that we said that each classification model must have some discriminant line or decision boundary. If you have just one line, you can see this central line here, then you have a few, I don't know, few values that are kind of a question mark. Some of them are closer to the line, some of them are far away, some of them are very close. So it's very hard to define or decide which one of them should be added to some class with high confidence and which one you shouldn't add to that class. And support vectors actually solve this problem by getting more in depth into this separation. So you have two support vectors and they're very close to these values that are hard to be decided or assigned to each class. So support vectors are important when dealing with these values that are hard to classify, and that's why they add additional layer of accuracy. You have another term here, support vector machines with linear kernel. If you already know something about the term kernel, then you probably had some experience with IT sector or programming or operative systems. If you don't, I will explain both of these things and something that we use in machine learning as well. Kernels are actually something that is a term generally used in computer science. So programmers use term kernel to describe those parts of the operating systems that are most essential because they're the first layer of communication between hardware and software. So hardware and software are communicating over parts of operating system that are called kernels. So they're like the basic parts of any operating system. In machine learning, in data science, we don't refer to this as kernel. So kernel is a completely different thing in data science. What is a kernel? Consider this left part of the image. You have x1 and x2, right? You have some values plotted based on those two dimensions. So x1 is one dimension, x2 is second dimension. In data science, you can create a third dimension. In essence, it's not a new dimension. It's just a third dimension that is derived from the interaction of these two first dimensions. So in essence, you can multiply x1 and x2 and then unsquare them, which is just a mathematical formula for what I'm speaking, and you would create this third dimension. So when you look at the model to the right, you have Z1 and Z3, which is the same as X1 and X2, right? Horizontal and vertical. But you also have this third dimension, Z2. And you can see in the formula that Z2 is created by multiplying Z1 and Z3 and then just unsquaring. So Z2 is interaction between Z1 and Z3. So we have two dimensions and we have their interaction. That interaction can be used to add also more accuracy and draw better discriminant lines. So you can see on that model to the right that actually Z2 is playing important role in creating the discriminant line. I won't bother you too much with the mathematical part, but I think that it's important to understand these terms, what SVM is, what kernel is, to continue the analysis. So I'll be taking you through the parts of the platform that can be used to upload the data, create groups, We said that test and train groups are always important thing when conducting supervised machine learning, and then create our first LDA pipeline. So we will get some outputs. You'll see that we'll have a lot of results from PDF files, from those uh, trained models, statistics, confusion matrices, and everything else. So I will just start here with the LDA, and we'll continue on other types. So I'll just share my screen. Okay. So can you please confirm that you can see my screen?
Yes, Darko, I can see it.
Okay, great. So let's go to the platform. You see we have, okay, thank you, Sarah. So we use the platform address and we go to that supervised analysis section. So you can upload two files that we send you. We sent you files that are named like this. You have these two files, right? So cell lines expression data train and cell lines expression data test. In essence, these two files are actually from the cell line project, but the first file that is called train has a large number of samples in it that we'll use to create a train model, and then we have more samples which are not present in the train data set, and we'll be testing the model on that one. So we go to group selection here, and we said that we must add the trained model to the train group and test to the test. So we'll create the pipeline. It's very simple. 3 steps. Go to LDA here. You don't have any additional parameters here, but you can read something about linear discriminant analysis and some things that we're actually talking about today. So when you take a look at this, you have the option to run decision tree here as well, but we won't be doing that right now. Okay, our team will send you the data set if you don't get it. So essentially you finish the pipeline, let's call it LDA session, right? So we run the pipeline and it will run in a couple of minutes. We'll get back to it, but I already have one prepared for you, so we can review it here. So if you look at the output files, you have these two files and you have one file with all results, right? So in that file, which is zip, you have all the output files from the LDA analysis. The point of the LDA analysis is to create a trained model that we can use to classify new objects or new data sets. So let's take a look at that trained model. Let's first download this into a folder. I will call it LDA session. So you will see that each of these files have some information that is important to the analysis. For example, we have prediction train, we have stat, we have test. Let's go over this one first. Predicted statistics. So this is like a general file. We saw that decision trees created a similar file, and for example, let's open it in Excel. You have that confusion matrix that might not be perfectly aligned here, but you can see the overall accuracy of 0.86. Now I'm going to open the same file in R. We had some issues when opening TXT files in R. You don't just run codes in R. You can open any file in R, right? You can open TXT file in R. So you just go here and under the file section, you go to the same directory. We're not actually running any code here, yeah? So we just go to that directory, which is called LDA session, and open. So So we'll set this as our working directory. So without running any code, I can just click on any of these files. I'll click on that same file, for example. It's used by another, okay. We have to close this one. So I can open it in R, and you can see it looks pretty much similar to the one we opened in Excel, but I'm just showing you a few ways. You can open it in Notepad as well, but you can open it in Excel or in R. So we have the confusion matrix. We have overall accuracy of the training set, which is 0.86%. These values that are here on the diagonal line are the cases that are predicted well. So basal to basal 9, that's good. Claudin to Claudin 3, that's good. Luminal 19, etc. etc. So this diagonal is showing us the objects that are predicted well. These objects that are here, they're not on the diagonal, they're not predicted very well, right? So for example, this one that is normal-like is predicted as Claudin low, or this one is predicted, luminal is predicted as basal, right? So we have bad predictions here. On diagonal, you have good predictions, and then you have, I think, 5 bad predictions here. But 5 out of all these, 9 plus 3 plus 19 plus 2, we would get 86% accuracy. This confusion matrix and this accuracy is for the thing that I was talking before, internal validation. So you create a model, you eliminate the labels, and then you test it on the same data, and you would get accuracy of 0.86. So it's not really perfect. It made 5 mistakes. For me, this would already be a concern, which could affect results on some other data. If you have 86% accuracy on the same data set, that accuracy could be even lower on different data sets. So let's see how could we, for example, increase this accuracy. You have some other outputs before I go there. You have the train model, which actually tells you what is the true class, what is predicted class, and how did we derive all these statistics. You also have the test statistics. This is statistics that is actually done on that test file, the second file which has no label. So we use that train model to predict the file with no labels. So each sample in that test file is actually predicted, and a class is assigned to it. So we have some predictive model here. We have samples, and then every sample is assigned with a class based on that predictive model that we created here. But as you saw, it actually made 5 mistakes there, so it's very realistic that we could also have mistakes here. How would we analyze that? Well, we would need to validate the trained model even more. How would we do that? Well, the simple approach would be to run more analysis, use more machine learning methods. But there is even simpler method, which is to use the same method, but use it in different forms. To show you what I'm talking about, let's run another algorithm. So we're uploading the same files. You can see that the pipeline is finished before we move there, LDA session, and the pipeline will create those same, will have those same results. So let's upload the files again, train and test. So after selecting the groups, we can run something that is called swLDA. So in essence, it's the same thing as LDA, but with one difference. What LDA does is it runs iterations, definitely. It creates a classification model, but it takes into account the whole dataset. There is another form of machine learning of using algorithms in machine learning, which is called the stepwise method. From the name itself, you can conclude that some steps are actually being run. And don't confuse steps with iterations. So each machine learning method has its own iterations. That's how machine learning is happening. But being stepwise is a complete different thing. So in general terms, each algorithm is stepwise because it has steps. It has, I don't know, prepare the data step, read the data step, then we have process the data, run the analysis, perform machine learning, and give the output. But that is some general term of being stepwise. In machine learning, in data science, when we say that something is stepwise, we mean that objects of the data set, for example, those genes, it could be samples, it could be genes. In this case, it's the genes, are being added one at a time. What I mean by that, you have the first iteration, for example, and in that iteration, you include just one gene to create a predictive model. And then you run second iteration, and then you include another gene. And then you run 1,000 or 20,000 iterations, including one gene at a time. What did we create when running a model in stepwise fashion is that we created a large number of models with every single gene being included or excluded. So that improves the probability of finding a more optimized model, a more accurate model, and a better classification model. So you have another thing here, which is called niveau, which is related to statistical significance, and you can also read information about it here. So let's, for example, set it to 0.001. So if we run the swLDA, let's call it swLDA session. It will run in the background and we'll get back to it again. But I also have two swLDS run before the session, so you can review the results. You have more results. You also have some plots here. We had the plots before. Let me just take you back to this file when we run the plain LDA. So this was the plain LDA, right? You have three LDs, so linear discriminants, and you could see that no matter what combination of them you take, LD1 to LD2, it's very hard to classify all of them. We can see that the luminals are separating, basals are separating, but some of them are overlapping, right? Separation is not like 100%. And that is why we had those errors in the classification. So this was the first LDA without being stepwise with 86% accuracy. But if we take a look at the pipeline that is just being run, I'm gonna review it after it's finished, but I have the one that is already run. You will get another PDF plot, which looks like this. Take a look at that. All of the samples are clustered very well. Separation is like 100%. You can even see that the text can be read for normal, for example, at this left part of the plot, because they're overlapping so much that you can actually see the letters. They're like overlapping nearly 100%. So this will definitely be a product of being stepwise, because when you include or exclude each gene at a time, you're reducing a lot of noise, right? So all those genes that could be noise, at some point they weren't included. So when you analyze all the steps, all the iterations, you definitely have models that have more accuracy, and those models are selected to be the final trained, to be part of the final trained model. So I'll just go back to the pipeline. It's still 33%, but I can download these files from this one until it's finished. So for example, let's take a look at, let's create another folder here, which is called swLDA. So if I download all results into that folder, swLDA, I'll be able to review them either in Excel or RStudio. For example, let's use the RStudio to review. We can review some in Excel, some in the RStudio. Let's review this one in Excel first, in RStudio, sorry. So we go to that directory, swLDA, and let's just review this one. swLDA prediction statistics. This will create a confusion matrix for us, and we can see it here. Take a look at that. All the diagonal cases are there, and none of them are away from the diagonal, right? So basal to basal 100%, clothing to clothing 100. Same goes for luminal and for normalized. Overall accuracy is 1. In probability, when something is 1, that's 100%. So swLDA has 100% accuracy on the same data set that we use to create the trained model. So self-validation produces 100% accuracy. One very important thing here is that when you get a result like this, it's based on, I don't know, this is 15, 35, 38 samples. When you have 100% accuracy on something like 40 samples, you have 22,000 genes, that's true, but we have 40 samples. That doesn't mean that this is universal model and it's always going to have 100% accuracy. But we have indications that it could be close to that. So we could have another 100 samples, but accuracy shouldn't be deviating too much from 100%. Maybe it could be, I don't know, from 95 to 100%. That would be some pre-expectation from me, for example. So if you get input like this, it means that the model is quite accurate. It doesn't have to be 100. I'm just repeating that because I know that a lot of you come from different sciences, and sometimes you don't need 100% accuracy, sometimes you do. So this is a very important thing here. This doesn't mean that it's always going to be 100, but it could be very close to that. So let's open some files. I don't know, some of you are using Excel. For example, let's open this one in Excel. So this is prediction for the test file, which has different samples, right? But they're unlabeled, and let's see how did our trained model classify. So let's open this in Excel. Take a look at that. Each one of those files, each one of those samples, sorry, is also assigned with a class. But we know that our trained model was 100% accurate on the same data set on self-validation, and as I said, we can expect high accuracy here as well. This is another data set that has 14 samples, and from my perspective, it should be either 14 are well predicted or 15 are well predicted. Now I have that data set. It's here. We have this cell line data set that has all of these samples, both from the train and the test data set. So in essence, it predicted all of them accurate, right? So 14 out of 14, all of them were accurate. So let's just get back here to some things we talked about: false predictions and good predictions on the diagonal, right? And then we can see that a new test set can also be predicted using that trained model, but it's not 100% accurate. But if we run the swLDA, we have a more accurate model, and now we can predict those classes with higher accuracy. So the important thing is that you can compare this one, for example, you can compare it to the first one where we had some inaccuracy, right? And you can see where are those inaccuracies coming from, which of the samples is critical to predict. And in the end, you would take predictions from this one because you know that they're more accurate. As I said, it doesn't mean that you're gonna get 100% accurate. Sometimes you could have one mistake from 14, for example. That would be my expectation. Sometimes you can have more. Let's use another method, which is called SVM. You have the explanation on the platform of those support vectors that are being expanded from the central line to be actually supported points to the clusters. And let's run that analysis. So we go to supervised analysis, we upload the files, and we select the groups to use the same two files for each analysis. What we're doing is actually creating more angles to this machine learning part, right? So we used decision trees last time, right? We used random forest. Now we use LDA, swLDA. We got different results here. Let's use the SVM. We talked about support vector machines. We said that kernels are actually those new dimensions that are derived from the interaction of the existing dimensions. So you also have other options here of using not just a straight line as a kernel, but also sigmoid, which is that line that has a curvature or radial or polynomial, but let's stick to linear for now, and let's finish the pipe. So let's call this one SVM session. Now, before I take a look at the results of this one, let's create another pipeline, right? So we can have another angle of validation. As I mentioned at the beginning of the first LDA pipeline, you have an option to actually expand LDA to decision tree, right? We run decision trees in our last session. So when you click here, you have an option to expand on decision tree, right? So you can add another dimension. You can run LDA and decision trees as well. This doesn't mean that they're being combined, right? You're just running LDA plus decision trees, and you will get two outputs. So we can finish this one and call it LDA decision trees, LDA DT, for example. And those pipelines will be run here. Before they finish, let's review our swLDA and confirm that we got those same results. So this is the one that we run during the session. And these two will be run. I'll use the same principle before they finish. I have some that I run here. LDA decision tree is run also before the session, and you get 4 results. So you have 2 RPECs, could be used in similar ways we used before to customize the plots and everything. But for now, let's review the results. So you have results from the, for example, decision tree. You can see decision tree here and LDA here. Let's review these from the LDA. So you have that same plot, right? You have TXT files, confusion matrices, and you have the statistics file. I'm just opening it in Notepad to see the overall accuracy. You can see 86%, right? But you also have this file, decision tree, right? So we run decision tree supervised method to also create another classification model. So when we go to statistics, we'll see that it's 0.92, right? So it's still not 100% accurate. So the one that performed best of all of these was so far was swLDA. It's the only one that had 100% accuracy. But my SVM is also finished here, and I can review its results, right? So you go to all results, and you have that same file, predict stat, right? Let's take a look at it. It's 1, right? So it's 100%. We can also open the confusion matrix here. I'm just gonna create a folder for this. So let's call it SVM, right? So and extract the files. So SVM is definitely very accurate as well. Let's open it in R. So SVM, and let's take a look at this one. This is the SVM. It's the same as swLDA. Take a look at this. It's not changing. It's absolutely the same. Because both swLDA and SVM predicted it in the same way, which was 100%. So now we have two models, swLDA and support vector machines. We said that both swLDA and support vector machines are very advanced forms of supervised machine learning. They have these additional features like support vectors, kernels, or stepwise nature, and both of them predicted it very well. So in essence, I would take this file either from the SVM, which I can open in Excel. The file would be the same as the one we had in the swLDA. It's the same predictions for the new samples for the test data. So we have samples and their predicted class. And this is the same thing we found in the SVM and swLDA. So I'll just get back here. I actually created a slide for this. So you have multiple of these. We also conducted swLDA, right? But it gave us these same results as SVM. So generally, this one was 92% accurate, this one was 86, this one was 100, as well as SVM LDA. So in essence, you would take this result and this classification for new data set or test data set. This would be the classification that would be most validated at this point. There are more types of validation. You could take more data sets. For example, you don't need to have just train and test. You could have a train model, and then you could have 50 test models, right? You could have 20 test models. The more data you have, the better. The more data you have for both training model and testing models, you will get more accuracy. So to be as close as possible to that optimal accuracy, you definitely need to have good. You need to have a large amount of samples, large amount of genes in your data sets, and when you have that, you can divide them in different train and test partitions, and you can also run multiple machine learning methods to validate the analysis signal. So validation is very important, and just repeating that from supervised machine learning perspective, because prediction models must be very accurate to be taken seriously, to actually do something, to predict something in a good way. If they have even small levels of inaccuracy, then they're not good predictive models. They could make bad predictions, and those bad predictions could lead to something else, some other errors in the data analysis. So I won't be going too much for now into these things that I was talking about. We have different levels of validation already. So right now I will just cover another type of, it's both unsupervised and supervised, similar to naive bias. It's not similar in the nature of the method, and I will please ask you to mute your microphone if you already haven't done that. So it's not similar from the method perspective, but it's similar to naive bias, both unsupervised and unsupervised machine learning, so non-labeled data, labeled data, and even images. It's called deep learning. I'm sure a lot of you already heard about deep learning, and it's actually a branch of machine learning, and there is a big debate of how to classify these branches, either to just unsupervised and supervised, or unsupervised, supervised, and deep learning, and then there is another form which is called reinforcement learning. So there's a big debate on how to classify it. But one very important thing is that deep learning uses artificial neural networks to create predictive and classification models. It also has this unsupervised nature. So it's both supervised and unsupervised. It creates, for example, it separates subtypes in the data, but it also creates classifications and predictions for it. It also selects important features within this neural network. And one very interesting thing is that a lot of these things that we actually had to perform on our own, we had to add some rules, some parameters, we had to add some methods that would be used. Those methods have their own rules. For example, I don't know, when we were performing hierarchical clustering, we defined, I don't know, expected number of clusters, and then we defined the method. It was word method, and word method has its own rules. And then we defined distance parameter and everything else. All other things were done by the algorithm, but we still had to use a lot of rules or methods to actually perform the analysis. In deep learning, a lot of these things are semi-autonomous, right? So a lot of those rules, different methods, different validation rules as well, are actually created inside the neural network. And we don't have too much to do with that. Neural network has its own code, how to start the model, how to create the network, but then a lot of things, most of things actually happen inside the neural network. So that's why we say that it's semi-autonomous. There are also other types of machine learning, like reinforcement learning, that are autonomous. So this feature of being semi-autonomous is very important because it makes less mistakes. It's very complex. You can see here that we have some first initial layer on the left with some input data. And then we have the second layer with letters H, which is called hidden layer, right? So all the information from each input is being fed to all other hidden layers. And then those hidden layers lead to another hidden layer, and again send all inputs to them. Another important here is we also have decision boundaries. So that is another feature that is similar to decision trees. If input reaches certain value at each of these hidden layers, then the signal is sent to the next layer. And then we have a network that is similar to neurons. Neurons in human brain function in a similar way. If this action potential, this electric potential that is occurring in the neurons reaches certain level, then that neuron fires and sends signal to the second neuron. And the same principle goes on. So that's why we call it a neural network. We have this threshold and firing principle between these nodes, which are called neurons in the artificial neural network. They're so accurate, and as I said, this accuracy can be used in very advanced data science. It can be used even for image recognition, and that is something that is very popular today, creating a neural network and then training it to recognize images or parts of images. Some research has been done lately in recognizing, for example, certain types of cells within the tissue using neural networks. So before I go to the next slide, I will just repeat this important feature of the neural networks, that learning, classification, and most importantly, validation, and a lot of other things are actually happening inside the neural network. We don't have to set those things on our own, and the classification is being created on its own, predictive model, unsupervised part of the learning, and that's why we call it semi-autonomous. That's why it's very powerful, because it can do a lot of these things inside the neural network. This is an example that I actually created of localizing proteins, whether they are in the cytoplasm or the membranous part of the cell, and you can see that actually you have these CPs and IMs, which stands for cytoplasmatic or intramembranous, and we can classify them based on some initial data, what is their location, and create classification model are. So, as I said, a lot of research is being done lately in, for example, biopsy image recognition using deep learning. So you have a whole slide tumor image, you have some microscopic images, and you use deep learning neural network to have a trained model that will recognize cells that are called TILs, or tumor infiltrating lymphocytes, and separate them from non-tumor infiltrating lymphocytes. They're very important because tumor infiltrating lymphocytes have the ability to recognize tumors. So potentially they could be used in therapies. Because one of the biggest issues with tumors and cancers is that they're kind of going under the radar for our immune system in a lot of cases, and they can't be recognized by immune cells. So if you have some cells within the tumor that have the ability to recognize it, perhaps they could be multiplied and then fed back to the organism to create some form of therapy. So a lot of research is being done in this. You have this exemplar project here with use of deep learning in identifying TILs. How can an image be recognized by a deep learning model? As I said, deep learning model does most of the things on its own, but there is one important aspect here is that pixels can be converted to numbers. They could be converted to dimensions. They could be converted to classes. Shapes could be converted to classes. Ratios within the image could be converted to classes. For example, I don't know, ratio between nucleus and the whole cell, right? So each feature of the cell can be created, can be assigned with a certain characteristic, and this characteristic could be used to create classes. Now, as I said, deep learning models are very accurate. They're not 100% accurate, just repeating that thing we had before, but they're very accurate. And you could use them, I don't know, to automatically recognize some cells when viewing the image under the microscope or some other type of imaging system. So before I go to this part, I will let you ask questions. You can unmute yourself or type questions in the chat. And please, if you don't understand anything or if you would want me to expand on anything, you can ask. Okay, Sunita, are you asking my Skype ID? Okay, here's my Skype ID. And here's my mail. So you have both. Okay. Okay. Okay, we'll talk about that. So you have both of my contacts and we'll talk about that. If you have any questions, please either ask in the chat or if we don't have the say, okay, if you don't have the test data, you can do a few things. If you, for example, run this code in R, you could have just test data. You don't need, you could have just train data, right? Or important issue here is you can't have just test data, right? Because in order to test something, you first must create a trained model and then test that model, right? So I understand your point, and it's a very good question. If you don't have test data, you just have the trained data, and you're right about that. So you can use just trained data to create a model, but it's always better to have a test sample to actually test it and see how it performs. But you could have just trained data and create a model. If you were to run that on the platform, you would need to take that same trained data set. If you have just one data set, you would need to take it and rename it. For example, you have a file that's called trained data, and then you copy it, right? So you go to save as and save it as the same file with a different name. For example, train data 2. And then you have two same files with same samples and same information. So you upload both of those files, one as a train data set, one as a test data set. So you can do that on the platform if you have just one data set. But also if you have a data set that is big enough, you can separate it on your own in two data sets. So one of them would be test or train. It's possible in theory. You could create just a train model, but you wouldn't be absolutely sure how would it perform on some other data set. So it's very important to have both test and train data. And in my opinion, ideally, you would have very large test data sets. So you would have, maybe they could be even bigger than the train data. There is this some rule of the thumb in machine learning to have at least 70% of the train data and then 30%. That is the minimum value. But you could have, I don't know, that same train model and then have 10 times higher test model. That would be better in my opinion. So test samples are very important and it's always good to have them. But if you don't have them, you can also create a train model and it could have some accuracy, but you wouldn't be really 100% sure how would it perform on different data. Okay, so Sarah, is there anything else that you would like to ask? Okay, okay, thank you, Sarah. Yes, that's actually what our team is telling you. So this is one aspect. You run multiple models. They're all classification models. They all create same output. You saw that they all create that confusion matrix, that test set. They all create the classification. So we get the same output from different machine learning methods, and we select the ones that are performing the best. In our case, it was swLDA and SVM. But there is another important dimension here, and this is especially for Sarah, as she was the one that mentioned it. If you want to create, someone actually asked a similar question before, what is the best model, right? So I will just expand on that a little bit. The best model would be the one that has the best data and all of these machine learning models used, right? So if you have huge amount of data, you have good training set with large amount of data, and then you have multiple test sets with also large amounts of data. So they would need to contain all the relevant data. You could also create multiple trained models and then compare them and see if they're similar. If they were all matching and they were matching across a large number of test sets, and they're matching on all of those methods that were found to be optimal, that would be a very, very good trained model. So you could have very, very high accuracy and very high confidence. But as I said, it's never 100%. In statistics, in machine learning, nothing is 100%. So generally, it has to do with the theory of probability, and probability of having something being 100% can happen only if you have infinity values. So if you have infinite samples, then you could have 100% probability. But as we know, in reality, nothing is infinite. We all have finite values in all aspects of physics or biology or science or anything. So nothing is 100%. Formula for the classification. You actually have that formula. That formula is more like a prediction model, right? So LDA, swLDA, and support vector machines will provide you with the classification output. You have information here. I will just go back to that, and you have a lot of results here, right? So, for example, if we go to LDA, you have outputs that are like this. You have this output, which is actually a formula for classification, but you'll see that it won't give you much of, this is the formula, right? This is used for classification. So each of the genes is set with the classification discriminant line, and then you compare them. But it's a big formula, as you can see. On the other hand, what is relevant to you is the formula that you would get from decision trees. So I will just, this is actually the one that we run on this session. So it's good to open it again and take a look at this. So you have decision tree plot, right? This is your formula for classification. If this gene is lower than 0.93, then you go here. And then if this gene is higher than 2.42, you go here and you got the basal. So your formula for classification is actually made of decision boundaries. And those decision boundaries are found by the algorithm using different formulas. But most relevant formula for creating the classification is actually the one that looks like this. So you have two genes and you have their decision boundaries. So if your value is this, then you go this way, or if your value is this, then you go this way. So you have that as some concept of how to classify each new case. And that would be something that relates to formula of classification. But as I said, different methods have their, like LDA here, for example, have different statistical properties that they use in the data. And as we said, some of them are less interpretable, some of them are more interpretable. In my opinion, the one that you get from the random forest or decision tree is actually the one that is most interpretable in this form of what is the concept of classification. So you have all the results, you have the confusion matrix, you have everything, but you also have this. You also have this concept of how to classify cases based on what genes and based on what values. Okay, so please, Sarah, if you need any more expansion on this, please ask me. Okay, so Vamshi. Okay, I see we have more questions here, so I'm gonna answer Pratim's first. Different data sets from the. Okay, so Pratim was actually answering your question, right? So this is actually the answer that Pratim told you. If you have different data sets, as we said, only something that is infinitely large sample will have ideal features. When you deal with lower and lower samples, you always have different and different results. So the more samples and more data you have, the more accurate and more confident your results will be. That's why we validate the data set on itself, and then we validate it on another data set, or we can validate it on more data sets with even more samples. The more validation you have, the more testing you have, the more confident you can be in the results. So Vamshi, maybe this is out of the topic, but I want to know, when do we use naive Bayes algorithm? Is there any significance to this type of data we can assume? Okay, so we had this, right? We were analyzing macrophages, and we said that we could compare samples. When we were running this analysis, we were actually classifying samples. We used those genes to classify them into different classes. So in essence, we were comparing samples. We were classifying them based on genes. But there is another approach. You can compare genes without referring to classes. You could just compare genes to each other. How do they behave across different samples? How do they behave across different timelines? So we had that 0 week, 7 week, if you remember. And then use those patterns to compare genes. Do they follow the same patterns? Are they related? So in the end, we use that naive Bayes algorithm to create a network of association between the genes. And I think it was this one, as far as I remember, that if you were to Google these genes, if you were to analyze them on NCBI or Firebros or Ensemble, you would see that a lot of these genes. Now, forgive me if I make mistake, but I think it was this branch of the naive Bayes that was actually for phagocytosis. And we had signals for phagocytosis, and then we actually had the phagocytosis happening and all those other things within these networks. So naive Bayes is very good for creating networks. You could create networks of samples. You don't need to create networks of genes. So you could have a large number of samples, right? You could have 2,000 samples, and you could create a network of samples. But in most cases, we have more genes than samples. So they're very effective in creating networks of genes. For example, a network of more than 15 or 20,000 genes could be created like this on T-Biome. So these networks are very often included in the publications. I actually reviewed a lot of research and read a lot of research that has naive Bayes networks uh, that are related, for example, to molecular signaling in cancer or molecular signaling in some other aspects. Okay, so I hope that, yeah, okay, so I hope that kind of clarifies it a little bit. It was a very good question, Vamshi, and I'm glad you asked it because I also wanted to explain another thing before we finish. I know it's taking a long time, but these are all important things. We want you to get some perspective on multiple aspects of data science. So from just doing statistics or applying it to a certain project to machine learning and to other example projects. It's a lot of things, and that's why it takes a bit more time sometimes. So forgive me from expanding a little bit on some issues, but I think it's very important that you have complete knowledge of some things. So naive Bayes, we run it, and you can see here that it's also in the supervised. We said that it's universal and that it can be used on both unlabeled and labeled data. So it's here under the supervised, but it's also under the unsupervised. Let me just tell you a few words. I won't be explaining Bayesian mathematics. It will be explained in one of the BioML courses, but let me just give you some basic information of what are the characteristics of this algorithm and why is it called like that. So in essence, imagine that you have these genes, right? And imagine that you have no relations between them. We said that these edges are some relations, green and red. Imagine that you had no relations. You just delete it, right? You have just genes. And that is what naive Bayes method does. It assumes that all the genes are independent, right? So there are no relations, but then it finds those relations. And by some statisticians, this is very debatable, but others actually think that it's improving the accuracy. And in my experience, naive Bayes was very accurate. But uh, some say, hey, we know that in biological systems, nothing is independent. Everything is dependent on something. So how can we assume that everything is independent? Is that an accurate analysis? But there is the trick here. Since everything is very complex and you don't really know what is dependent on what directly. Something could be dependent on something just because something is dependent on something third, right? So it's very hard to create a hierarchy of dependence and include that in the algorithm. So naive Bayes actually simplifies everything. It says, hey, nothing is dependent. And then let's find those dependencies from the data. So that's it. It has this unsupervised form because it assumes no dependencies. It derives everything from the data. On the other hand, you can use it to classify all of these. It's not a typical classification algorithm, but right now I can, for example, classify these genes as being a part of some signaling network or being a part of some process or being connected to something. So in essence, it's both unsupervised and supervised, and it's called naive because it assumes no dependencies in the data. This other part of the name, Bayesian, it refers to this mathematical model, Bayesian model, and as I said, this is expanded in the machine learning BioML course, BioML 2. which will be up in some period after this. I believe during the program that BioML2 will be up. So if you wish, if you feel the need to expand on some of these methods, there will be also a machine learning course, multiple of them that will expand on those methods. So it's about 10 to 6, and I believe we should be finishing here. So I'm leaving my email again. If I saw last time that some of you actually asked me some questions, and I will use this opportunity to actually type this line of code for you. So wait a second.